Hello class, welcome to this video on 6.1, discrete and continuous random variables. So we're just going to kind of finish up the lesson here. There's a lot going on in this chapter, but we do need to get through it. We had talked about learning target number 1, and we said, which is about probability distributions of a discrete random variable. Discrete means that you're looking at whole values or gaps between values, right? So you're looking at a fixed set of values. And so here we have a sample space for tossing a coin 3 times. If you toss a coin 3 times, there are 8 possibilities, three heads, 3 tails, and anything in between. And the probability of each outcome is 1/8. So this defines a probability distribution. Well, what we're going to do is we're going to actually record this in a table using a random variable. So a random variable is a variable that takes on values that describes outcomes of a chance process. So it's random. And so we're defining x is equal to the number of heads. And so in this experiment, there's only 4 possibilities for the number of heads: 0, 1, 2, or 3 heads, right? And so we can put that in a table and summarize it as follows, saying that, okay, well, 0 heads, there's only one way to get 0 heads, which is 3 tails. There's only one way out of 8 to get 3 heads. And there's 3 ways to get 1 heads, right? So there's 1, 2, and 3 here. And so on and so forth. And this becomes a probability distribution. And so it gives all the possible values and all the probabilities. And so we use capital letters to designate the random variable. So here, this is a capital X here. But when we're saying a specific value of X or a specific value of the variable, we use a lowercase. If you notice that right there. Okay, so there are 2 main types of probability distributions. We mentioned discrete, and then the next one is going to be continuous. Okay, so discrete is fixed values, and continuous, it can take on any value in an interval. So for example, height, time, things that you measure tend to be discrete or continuous. Things that you count tend to be discrete. Okay, that's what we had talked about. And and then example 1, we went through the example with the three coin toss, the tossing the coin 3 times. So if we want to, for example, get the probability of getting at least 1 head, then that means it's greater than or equal to 1 head. So that means you can have 1, 2, or 3 heads, right? So x equals 1, 2, or 3. And so you're going to need to add those together. Okay, so then you get 7/8 if you combine these together. But you could also do 1 minus 0 heads, and you would get the same answer. So that's this part B right here. Okay. All right. So and then then we did the check here. So the check was about the APGAR scores, and from 0 through 10, and these are the probabilities. And you're trying to find the missing probability. So to get the missing probability, the probabilities have to add up to 1. Okay, so we add these probabilities up together, subtract from 1, and you get that. And if you wanted to get 7 or more, you just add these numbers up: 7, 8, 9, or 10, if you wanted at least 7 for the baby to be healthy. Okay, and that concludes learning target 1. Just quickly summarizing that, or going through that. So now learning target 2. Make a histogram to display the probability distribution of a discrete random variable. So Pete's Jeep Tours offers a popular day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to 6 passengers. Pete charges $150 per passenger. Let C equals the total amount. So this is the random variable here, capital C, the total amount of money that Pete collects on a randomly selected trip. The probability distribution of C is given on below. So this is a probability distribution. We're going to make a histogram, so that's all we're going to do here. All right, and then we're going to describe the shape. Okay, so we're going to say, in this case, right, we're going to say C is going to, the x-axis is the random variable C. So C equals the money collected. All right, and then so here we got 300, 450, 600, 750. So I'm just going to go, I'm going to say 300 here, 450, and I'm just going to do 150 here. All right, so we got those values there. And then the probability, so probability goes on the y-axis. All right, and then, okay, so and all you gotta do, so here for 0.15, we have 300. So, and they're over individual values, okay? So let's scale this. So 0.1, 0.2, 0.3, 0.4. So 0.15 will be around here. You get 0.25 around here. And 0.35. Remember, in a histogram, the bars have to touch, okay? So they have to overlap, to touch each other. And then 750, we have 0.20. And then lastly, 900 is 0.05. Okay. All right. And so what's the shape of this distribution? It appears to be roughly symmetric and has a single peak. So it's unimodal and has a single peak at 600. Okay. All right. So the shape of distribution is roughly symmetric. And unimodal with peak at 600. Okay, so just pause the video and see if you can make the probability distribution for the previous problem. With the APGAR score. Okay, so the so I guess I should put the APGAR score, the APGAR problem. Okay. All right, so hopefully you tried to do the histogram for the APGAR data, which is right here on the left. Okay, so all right, so we're going to make x is equal to the APGAR score. APGAR score. And we'll just start 0 here. 1. Okay, so 0 to 10. And then now if you look at the numbers, the highest number is 0.437. So I'll just go up to like 0.5 or something like that. Okay. You could do this. You don't have to do it this way. This is just one of the ways. And, I'm just scaling it by 0.1. But if you have a different way to scale it, that's fine. Just make sure you label your okay, so you label your guys. All right. And we'll go ahead and make the graph. So we figured out that for 0 it was 0.001 from before. So it's really small. And so on and so forth. All right. So here's how your graph should look like if you completed it. So we got really, really small values here, and it's just slightly going up, and then it peaks here, and then it goes back down. So if you your graph looks like that, you can verify. So the shape of the distribution is skewed left to the left and unimodal with a peak at 9. Looks like the peak is at 9. All right. That's learning target number 2, pretty straightforward. Learning target number 3 is calculate and interpret the mean of a discrete random variable. All right, so consider the random variable C, which is what we talked about before with Pete's Jeeps, right? Now, what's the average amount of money that Pete collects on these tours? And so what we want to do is imagine that we have, for example, 100 trips. Pete will collect $300 on, and if he had 100 trips, Pete would collect $300 on, well, it's 0.15, right? So 0.15 times 100, that'll be 15 trips, right? So on 15 of these trips, he would collect $300. For the 450, he's going to collect 20 on 25 of the trips. He's going to collect 450, right? Because 25%, right? So it's going to be 25 trips for 100 trips, and so on and so forth. 35 per trips, he's going to collect 600. 20 trips, he's going to collect 750, and 900 on 5 trips. And so what we could do is calculate the average amount that he collected for these 100 trips, right? So we can do 300, and there's not that much room here, so I should I'm gonna put it like let's see, yeah, there's not that much room here, so let me make sure I write it small here. So we got 300 times 15 plus 450 times 25, because he did it on 25 trips. So on 25 trips, he's got $450. So that means you have to multiply by 25. Otherwise, you'd be adding 450 25 times, and we don't want to do that. And on 35 trips, you have 35 600s, right? 35 600s. And then you have all right, we got 750. We have 20 750s, and we got 5 900s. Okay, and we got to divide that by 100 because there's 100 trips, right? And so another way of looking at this, and again, this is where I got to make this super small. Apologize. Is we can look at it as 300 times 15 over 100. Because we could distribute the 100 to each of these numbers, right? 15 out of 100, 25 out of 100. That's exactly what I'm going to do. Again, sorry for the little amount of space here. 750 times 20 out of 100, and then 900 times 5 out of 100. Okay. So that's what we got so far. Just zooming in on that. And so 15 out of 100, that's just a decimal. That's 0.15, right? And that's 0.25, that's 0.35. So we have 300 times 0.15 plus 450 times 0.25 plus 600 times 0.35 and 750 times 0.20 and 900 times 0.05. And if we add those together, we get $562.50. All right. And notice that the numbers that we have are the 0.15, the numbers that we use, 0.15, 0.25, are the numbers from the probability distribution, right? And so what we just did is we just basically took the value here and we multiplied it by the value here. And then we just multiplied those values and then added them to the other ones when we multiplied the other ones, okay? And then we multiply these, and so on and so forth. That's what we did, and we combined them. So the mean of the distribution we said was $562.50, and the mean is mu, so mu C. This is also known as the expected value. So the mean of a random variable is known as the expected value, and which is also denoted by an E. Okay, so in this case, it's E of C because C is the random variable. Okay, so these are some terminologies that you should know. So in this case, we would say mu c is the same thing as E of c, okay, the expected value. All right, so there's some lingo there. But now we know how to calculate the mean or the expected value, okay? In order to do that, well, it's just the average, right? So we calculated was an average. So it's the average over many, many trials of the same random process. So suppose x is a discrete random variable with the following probability distribution given by this table. To calculate the mean or the expected value of x, we would have to basically multiply x1 times p1, x2 times p2, and x3 times p3, and so on and so forth. And then we would have to combine those results, right? So in other words, so let me just kind of show you that. So we have x1 times p1, and they call it p1 here, but I'm going to call this p of x1 because that's what the AP exam uses. Okay, so I'm going to call it p of x1, p of x2. Okay, so that's what I'm gonna use because that's what AP exam uses. Plus x2, p of x2, dot dot dot. Okay. So in other words, the formula is simply the sum, that's when you add, of when you multiply x and p. So xi times p of xi. Okay, the sum of I. And we don't really need to include the sum. Usually I just do it like that. But this is essentially the formula, guys. This is the expected value formula, okay? You multiply the x with the probability, and then you add the results together, okay? All right, so interpretation number one, there's two ways you can interpret this. The first interpretation is if we can say if we randomly selected many Jeep Tours, then P will make an average of, in the case that we had, was $562, right? He'll make an average of $562.50. I really should have put this here. I'm sorry about that. This shouldn't be a blank here. Per trip. All right, and then the alternate interpretation comes from thinking about the probability distribution as a model for the population, okay? So if you think of the population of the probability distribution as a population, that's why we use mu here, because mu is for population, right? We usually use x bar for a sample, notice. So the reason why we use mu is because we think of the probability distribution as a population, all right, not a sample. And so if we think about it that way, we can interpret it as follows. For all of the Jeep Tours, the average amount of money that P collects on a trip is about $562.50. So either one is appropriate. So recall that the mean, so now that's the interpretation. So now let's look at the mean, okay? So this is the probability distribution for P. This is what we drew earlier in that one example. And the mean is right here, located here. Remember that the mean is the balance point of the distribution. Since this is approximately symmetric, it's close to the 600 peak, right? So that makes sense. It's pretty close to that. So that's the mean. And remember that the mean is the balance point, okay? So it's what balances the data, all right? So here we got, so here we got mean is the balance point. Okay, so earlier we looked at the Apgar score. So what I want you to do is calculate and interpret the expected value of x. And you can use any interpretation, or maybe try using interpretation number one, just so that if you want to compare the result, because that's what I'll be using. Okay, so hopefully you paused and tried the question before. All right, so calculate and interpret the expected value of x. Now, I'm going to show you how to do this on the graphing calculator as well. When you have a lot of points, sometimes you want to use the graphing calculator function for it. So we're going to show you how to do that, but before we do that, we're just going to show you the formula and all that, okay? All right, so the expected, let's see, we got the expected value of the random variable x is equal to, remember, it's the sum of when you multiply. So you multiply this, multiply that. So we have 0 times 0.001 plus 1 times 0.006 plus 2 times 0.007 plus ... We don't have to write all of them down, but I'm going to write to the last one. The last one is 10 times 0.053. And when we do that, we can just do that with a standard calculator, although it'll take some time. You get 8.128. And so if we want to interpret this, we would say, using the first method, if many newborns are randomly selected, their APGAR scores will be about 8.128. All right, so let me show you how to do this on the calculator. Okay, so this is on the graphing calculator, the TI. So what you'll want to do is you'll want to go to stat like we normally do, edit, and you'll want to put your data for your APGAR scores on the for X values, the score on one list, and then the probabilities on another list. Okay, so 0 to 10 here, and then the other probabilities here. And then once you do that, you'll want to go back to stat and then calculate, and you're going to go to 1var stats. You're going to make sure that this is list 1, and then which is usually there by default. Now this is usually blank by default, so let me clear that. So that's usually like that. So what you'll want to do is you'll want to go down to that, and then you're going to want to select list 2. Okay, so to do that, you're going to hit second and then stat to select the list here, and then go down to list 2 and enter. Okay, that'll give you the both lists, and then it'll calculate it. Okay, so hit calculate, and then there's your X bar, which we call mu, right? 8.128. So that's exactly what we got. Okay, all right, so there's that. So that's what we got, 8.128. And so now let's talk about the median. We talked about the mean, so now let's talk about the median. Okay, so the median of a random variable, of a discrete random variable, is the smallest value for well, the median in general is in the middle, right? So we call it the midpoint of the distribution. So we call it the median, the midpoint in the middle number. So the number such that half of the observations are smaller and half of the observations are larger. That's the traditional way we define it. And it's known as the 50th percentile. So when we're talking about a discrete random variable, the median would be the smallest value for which the cumulative probability, cumulative means you add up the probabilities as you go, so it's the smallest value so that the cumulative probability equals or exceeds 50%, or 0.5, 0.50, right? So the median amount of money in this example, so let's calculate that. So what's going to be the median for the Jeep's Tours example? Well, remember, this is the money he made, and this is the probability, right? So what we're going to do is we're going to add the probabilities as we go. So here there's really nothing to add, so let's just bring this down. So that's going to be 0.15. But when you get to 0.25, you're going to do 0.25 plus 0.15. So you're going to add those up. And so you get 0.40. When you get to 0.35, well, then you got to add these up, right? So so that's going to be 0.75. And then when you get to 0.20, of course, you're going to have to add these up. 0.95. And then lastly, 1, right? 1.00. Now notice that we don't have a 0.5, but we have a 0.4, and then we pass 0.5 to get a 0.75. And so since we passed 0.5, we're going to use the smallest number where we pass 0.5, which is this right here. And so that means that the median is going to be $600 here, okay? All right, so hopefully that made sense. And that's going to be what we call the median of this distribution. All right, so that's just a side note. So let's look at learning target 4, calculate and interpret the standard deviation of a discrete random variable. For random variables, so we're going to look at the standard deviation. We looked at the mean earlier, so now let's focus on the standard deviation. But let's, real quick, we know that the mean is typically used to measure the middle or the center of a probability distribution. So if we wanted to measure the variability, we would use the standard deviation. The variability is the spread. Oops, standard deviation, not deviation. All right, it's typically used as a measure of variability. All right, so what we want to do to calculate the standard deviation is we want to calculate a weighted average of the squared deviations. So we want to take remember the deviations are how far are each value from the mean, right? So the deviations are the x values minus the mean values, and the mean values is mu x, okay, the mean value or the expected value. And we're going to square those deviations, okay? And we're going to do a weighted average of those guys. Weighted average means you're going to multiply them by a weight to average them, okay? So you're going to multiply. So you're going to do the weighted average of these squared deviations from its mean, and the mean is mu x, right? So the probability distribution gives the appropriate weight that you're going to use for each of these squared deviations. So this weighted average that we're talking about of squared deviations is called the variance of x. If you take the square root of this variance, that gives you the standard deviation. Okay. All right. So we're gonna show you what this formula is, but first we're gonna formally define the standard deviation. I was just explaining the process. So now let's formally define it, and then we'll talk about the formulas for it. Okay. All right. So the standard deviation of a discrete random variable, it measures how much the values typically vary from the mean in many, many trials of a random process. Okay? All right, remember, this is probabilistically based. So because it's a probability, we have to use the law of large numbers. And so we have to do this over many, many trials. Okay? Okay, so suppose x is a discrete random variable with the following probability distribution, right? And again, they use P1, P2, P3, but in the AP exam, they use P of x1, P of x2, P of x3, okay? So on and so forth. So we're going to use that notation, all right? So we know that the mean or the expected value of x is mu x, right? The capital X. Okay. So now we're going to write the formula for the variance, okay? So what we're going to do is a weighted average. So a weighted average is when you multiply the weight, and here the weight is going to be the x values, okay? So that's going to be the weight, all right? And we're going to multiply that by the deviation, okay? So we got the deviation here, so let's write the deviations. The deviations are xi minus mu x squared. That's the squared deviations, okay? How far is each value deviated from the mean? That's what's called a deviation, and it's a squared deviation. And we're going to multiply that by the weight xi, which is the x value will be the weight, okay? And then we're going to average those together, so we're going to add those together like that. And then we have to multiply by the probability of the occurrence, okay, of each x value. Okay, that right there, oops, I'm sorry. Oops, I'm sorry. I said that we multiply by the x. That is incorrect. I'm sorry. We just multiply by the p. Sorry, there's not too many. We don't want too many terms in there. I apologize. So we're not multiplying by the x. We're multiplying by the p. Okay, which I wrote there, but I forgot to erase the x. Okay. All right. So we're taking the squared deviation and we're multiplying it by the probability, which makes it a weighted average. Okay, so I incorrectly circled this, right? I should have been circling the probabilities. That forms our weights, okay? All right, so we're gonna do the sum of this in order to get a weighted average, okay? All right, so there's our variance, and then we can take the square root of that in order to get the standard deviation. Okay, so this is the variance. So the symbol for that is sigma squared x. Okay, so if we want sigma x, which is the standard deviation, we just have to take the square root of sigma squared x. Basically, take the square root of this formula, right? Square root of the sum of the squared deviations times their individual probabilities. Okay, so there's the official formula, but really, we're not going to really calculate it by hand. I'm going to show you the calculation that you would do by hand. However, we're going to be using a calculator for this, okay? I just want to walk you through the process so that you understand how it works, okay? But we're not going to actually do it by hand, really. We're going to be using the calculator. Okay, so find the variance and standard deviation for the random variable C for Pete's, okay, for Pete's Jeeps tour. Okay, so we got the total calculated, we got the probability. I put it in a vertical format rather than horizontal, so these are the same values. Now what we're going to do is we're going to first figure out what the mu C is, right? But we already figured out what that was. We said that was mu C. We calculated that to be $562.50, okay? So we calculated that earlier, and we're going to do the squared deviation. So subtract the 300 minus the mean, and then do the same thing for the 450 minus the mean, okay? So I'm just going to illustrate a couple of these. I'm not going to do all of them. Okay, so 300 minus 562.5 squared, and then 450 minus 562.5 squared. So just take the C value minus the mean squared. Okay, and then dot, dot, dot. And get those values. Then we're going to do the weighted squared deviation. So when we multiply this column by the probability, okay? So we're going to do the 300 minus 562.5 squared times the probability of 0.15. Okay, this is the probability for that. All right, and then and so on and so forth. I'm going to show you the last one. 450 minus 562.5 squared times the probability was 0.25 for that one. So on and so forth. All right, so when you calculate this, you get 10,335.94. This one you get 3,164.06. And I will give you the rest of the numbers just so you have them as a reference. And we got 5,000 for the last one, 695.31. All right, and so now what you're going to do is you're going to add these together. So you're going to do the sum, right? And you get 26,718.75. And that, folks, is your variance. Okay, so sigma squared x, or not x, it's sigma squared c, right? Because c is the random variable, is $26,718.75. Okay, and that's in dollars squared because it's squared here. So if we wanted to in regular dollars, we would have to take the standard deviation. Okay, so this is so then we take the standard deviation, take the square root of that. And that would give us in dollars, $163.46. Okay, and that's the basic rundown of the process, guys. So that's how you would do it. But again, we're going to use the graphing calculator for that. We don't have to do that. So let me show you that real quick. Okay, and we're not going to use this for Pete's data. We're going to actually do this for the APGAR score. So that way I don't have to change the list. But so we're going to go stat, edit, and remember the APGAR scores that we had from 0 to 10, and then the probabilities. So I'm just going to keep those. And then remember when we went to stat calculate, we went to one var stats, and then we selected list 1, list 2, right? We did that by doing second stat and then selecting the list. All right, oops, let me go back to that. Sorry about that. And then you're going to go to calculate. Now, when we calculate this, the sigma x is right here. So this is for the APGAR score. This is not for Pete, okay, for Pete's Jeeps. But this is how you would find it. Remember, we had 8.128 for the APGAR score, the mean, okay? Okay, so now that we got that out of the way, let's go ahead and do interpretations for the standard deviation. Okay, because we want to be able to interpret it. A lot of stats is being able to interpret the data that we have. Okay, so the interpretation number one is if many trials, in this case many Jeep tours, are randomly selected, the amount of money that Pete collects typically varies. That's the verbiage you want to use, right? Typically varies, or on average it varies by about $163.46 from what? From the average, right? From the mean, and the mean was $562.50. Now, interpretation number two is thinking of the probability distribution as a population. And so you can say for all of the Jeep tours, the amount of money Pete collects on a trip typically varies by about $163.46 from the mean of $562.50. Okay, so that's what we got. All right. All right, so go ahead and pause the video and try the check. I showed you how to do this on the calculator, but you can practice it and show the calculation. All right, guys, so go ahead and hopefully pause and try it. So we got the mean, 8.128, and so now we're just going to calculate this. Now we already have the value that we showed, from the calculator. So I'm just going to use the calculator value, but we're going to show our work here. Okay. All right. So first we got to calculate in order to do this. Now, you're probably asking, well, how do I do this without a table? Well, we did the table to make it simpler, but really what we're doing is we're just basically writing these terms here on a single line. Okay. So let's just show you how to do it. So sigma squared. Now you could have done this on the side, on a table on the side, and then gotten that too, because I don't think you have enough space for a table because 10 values here. But you do have enough space to be able to do this on a single line, dot, and then just write dot dot dot. Okay, so here we go. All right, so again, we're doing the deviations. The mean is 8.128. So we're going to do 0, that's the x value, 0, minus 8.128 squared times the probability, which is 0.001, that's the first one, plus, and then now we're going to do 1 minus 8.28, 1 minus 8.128 squared, that's the squared deviation, times its probability, plus dot, dot, dot. And then all the way to then this one, right? So 10 minus 8.128 squared times 0.053. Okay, you see how I do that? And that's really, it's just dot, dot, dot. And then I can just figure out what that value is and take the standard deviation of that, okay? So, all right, and so, okay, so then the sigma x is equal to the square root of that value, and then we can use the value from the tape, from the calculator, okay? Right, and as you recall, the value from the calculator is 1.437, okay? So we can use those. I'm just going to use those 3 decimals, 1.437, okay? All right, so then we'll just interpret it, right? So then all we have to do now is, and by the way, yeah, so then that's what we got. And then, so we're going to use interpretation number 1. So if many newborns are randomly selected, the baby's APGAR scores will typically vary, there's that verbiage, by about 1.437 units, or right, from the mean of, and the mean was 8.128. Okay. All right, there you go. Learning target number 4, done. All right, so learning target number 5, use the probability distribution of a continuous random variable, uniform or normal, to calculate the probability of an event. All right, so for discrete probability distributions, we can find probabilities between values by adding probabilities of each individual value. However, when you're looking at continuous distribution, it is not possible because there are infinitely many possible values between any 2 values, right? There are infinitely many values. So like, for example, how many values are there between 1 and 2? Well, there are infinitely many values, 1.01, 1.0000001. I mean, you can keep doing that forever. So there's infinitely many possible values when you're thinking about mathematically between any 2 values. So it's a little harder I would say a lot harder, infinitely harder, for a continuous probability distribution to do that. So what we're going to do is we're going to describe the probability distribution of a continuous random variable by something called a density curve, okay? Density curve, okay? We talked about density curves before in chapter 2. So remember that a density curve has an area of 1 underneath it, which makes sense because if we think of probability as adding up to 1, then we would need a density curve to explain something that has to do with probability, right? So that makes sense in that sense. But we use areas under the curve to assign probabilities, knowing that the probabilities all have to add up to 1 because the area under a density curve adds up to 1. All right, so let's go ahead and look at an example of this. So let the continuous random variable y equals randomly generated number between 0 and 9. Okay, so you just randomly generate a number. Draw the probability distribution. Now remember that in this example, each number has the same chance of being selected. And so this distribution is actually uniform, okay? So it's flat, okay? Every number has the same chance of being selected. So we have from 0 all the way to 1. Okay. So there's my guy. And of course, I made the line, long, but you can spread it out if you want. All right, and then my probability, my curve is going to be flat because it's the same chance of being selected. Okay. Remember that this is the probability of being selected. This is a probability distribution. Okay. So it's going to be the same chance everywhere. Now we need to figure out what the height of this is in a second, but so we'll find that in a second. But we know that the x value, that this is equal to y, which is the random number, right? Between 0 and 9. Okay, so it's a random number between 0 and 9. Okay, so now we know that the area of a density curve has to be 1, right? Now we got ourselves a rectangle, so the area of a rectangle is base times height, okay? And we got that the base is 9, right? So the base is from 0 to 9, which is 9, okay? And the height, we need to figure out what the height is. So height equals, so let's call it h, but we know it has to be 1. So let's solve using basic algebra, divide by 9 on both sides. And so the height has to be 1 over 9. Okay, so there you go. So there is my probability distribution, my density curve, okay? So 1/9, and then there you go. That's what I got. Okay, so now that we know what a probability distribution of a continuous variable look like for this example, we're going to find the probability that we have that the random variable has a value between 3 and 7, including 3 and 7, right? So in order to do that, we would have to, well, let's just label it on this curve, between 3 and 7. All right, there you go. And then we're going to find the area underneath this part. Okay. So the area is easy. I mean, you just do the base is 7 minus 3, which is 4. 7 minus 3, that should be a 3 there. And then the height is 1/9, right? So you find the area of that. That gives you the probability between 3 and 9. Okay, so that's what we're going to do. All right, so the area or the probability is 7 minus 3 times the height of 1/9. So it's going to be 4/9, which is 0.44, going on forever. All right, so then what's the probability that y is equal to 7? Let's look at that. The probability that y is exactly 7. That means we're exactly here. But notice that if I'm exactly there, I can't be anywhere else. I have to just be there, right? And so is there an area corresponding to this line right here? Well, no, a line is infinitely long generally, but it has no thickness. A line shouldn't have any thickness, right? So there really is no area for 7 at a specific value. There's an area between two numbers, but there's no area at exactly one number. And so the area at any individual number, just at that number, is always going to be 0, okay? So if that's the case, does it really matter that we have a equal sign here? Well, no, it doesn't really matter because the probability at that particular number is always going to be 0. And so the whole point of this little exercise is to show you, hey, we know how to calculate these probabilities, but we also have to realize that it doesn't matter if you have the bar there or not. It's still going to be the same thing. So we can easily have written this as, for example, less than and then less than equal to, or less than equal to and less than, right? Or both of them being less than. It doesn't really matter, okay? The probability is still going to be the same, okay? 0.444, going on forever. All right, that was the purpose of that exercise for that part C exercise. All right, so let's look at, so go ahead and pause the video and see if you can try the Salinas example. All right, folks, so hopefully you tried it and you drew your density curve and all that. And if you felt like you weren't comfortable with it, you did it off to the side. So that way, just in case you didn't want to erase or whatever. All right, so Selena works at a bookstore in the Denver International Airport. She takes the airport train from the main terminal to get to work. It says Selena would have to go from the main terminal to the bookstore. She'd have to walk in 4 minutes. Okay, so allow her to get there in 4 minutes, but she wonders if it'll be faster to walk or take the train to work. So let y equals the journey time to work by train. Okay, so let's do that. So y equals journey time to work by the train in minutes. Okay, that's y. On a randomly selected day, the probability distribution of y can be modeled by a uniform density curve on the interval from 2 to 5 minutes. So they actually give you that information. So let's do that. So we'll start 2 here. And we'll just spread it out. 3. Yeah, we'll do 1, 2, 3, and then we'll do 4 here, I guess. 2, 3. Actually, I don't want to spread out that far. So let me 1, 2, 3, 4, and then maybe 5. Okay, something like that. And it's uniform, so it's going to be flat. All right, and it's from 2 to 5 minutes. Okay. I'm just doing the line so you know it stops and ends there. And we want to figure out what the height is, right? Of course. So we got to figure out what that is. All right, so we know that the area has to be 1 and it's base times height. And the base is 5 minus 2, right? It's from 2 to 5, so it's 3, the base. And that is going to have to equal 1. So we get 3h equals 1. So if I divide by 3, I get 1/3. So this has to be 1/3. Okay, there's my density curve. Now find the probability that it'd be quicker for Selena to take the train than to walk that day. All right, so it says there's a walkway that would take her 4 minutes to walk. So we want to compare that, the train rides, to the 4 minutes that it would take her to walk, right? So find the probability that it'll be quicker to take the train. That means 3 minutes, 2 minutes, anything less than 4, right? So we're looking for the probability that y is less than 4. That's what they're asking for, okay? So the probability that y is less than 4. All right, so then, okay, so then that means we're going to need this. We're going to go, this is the y value of 4, and we want it to be less than that. So we want to figure out this area right there. All right, so that area, well, it's from 2 to 4, so the base times height, 4 minus 2, times the height of 1/3. So it becomes 2/3, which is 0.667. All right. Sorry about that. Let me just write it out. Okay. All right, so there you go. That's your probability. So now let's look at another example of a continuous distribution, the normal distribution. Okay, we've seen the normal distribution before in chapter 2, right? So let's go back to that. And this is going to represent a continuous probability distribution. Okay, so the heights of young women can be modeled by a normal distribution with a mean of 64 inches and a standard deviation of 2.7 inches. All right, so the mean is 84 or 64. Remember, the mean goes in the middle, right? So we got the mean in the middle. The standard deviation is 2.7, so we're going to be adding and subtracting by 2.7, okay? So 64 plus 2.7 is 66.7. Add another 2.7, I have 69.4. And then one more time, 72.1. Now take 64, and then on the left, subtract 2.7, 61.3. Can keep subtracting 2.7, 58.6, and then 55.9. Now this, oops. Okay, sorry, go back to that. So this axis represents the y equals woman's height in inches. Okay, so now we want to find the probability that a randomly selected woman has a height of 68 to 70, okay, including 68, including 70. But again, it doesn't matter if you include it or not. right? Because it's still going to be the same probability. So between 68 and 70. All right, so then 68 is like around here, right? So that's y1 equals 68. And then we got 70 right here. Y2 equals 70. We want to find that probability. All right, remember that we find this probability in several ways. We can calculate z-scores, right? And then from those z-scores, we can find them in the table, right? We can also use the calculator to do this. So again, going back to what we did back then in chapter 2, we're going to show you both ways just to make sure you remember. All right, so let me show you how to do this here. We have some space here, so I'll show you how to calculate it. All right, so remember that the formula for the z-score is x minus mu divided by the sigma, right? Obviously, we're going to be using y and not x, right? But that's just the formula, okay? So that's just a general formula. So let's calculate z1. So z1 is going to be the y minus 68. So the first value was 68 for the woman, 68 inches and height, minus the mean was 64 over the standard deviation was 2.7. Okay, so this is about 1.48. And then we're going to calculate Z2 as well. So Z2, the other height was 70 inches minus 64 divided by 2.7. So you got 2.22 inches. All right, so now we're going to look these values up. So first off, remember, you look them up. If you want to find the area between two z-scores under the normal distribution, you have to look them both up and then subtract them, okay? So the probability that's between them, we have to basically look them both up and then subtract them, okay? So that's what we're gonna do. So remember that the table gives you the area to the left by default, right? The area to the left. So when we look this up, we're obviously going to need to look up both values, and then when we look up both values, we'll just subtract them. But just remember that it gives you the area to the left by default. Okay, now these are negative values, so we're going to need to look up in the positive values here. Okay, so we need to look up 1.48. Okay, so 1.4, and then 8, right? So 1.48 is right here between, that's the 1.4, that's the 8. So 1.48 gives us an area of 0.9306. And then let's look up 2.22. So we got 2.22. That's going to be right here, 0.9868. So then we're going to subtract those two values, and that will give us the probability we are searching, okay? All right. Okay, so let's go ahead and calculate this. So we said it was 0.9, right? 868 minus, this one was 0.9306. So you subtract those, you get 0.0562. All right, so how do we do this on the calculator, okay? We'll show you how to do this on the calculator, but remember, on the calculator, we have to use the normal CDF, okay? So let me do that here. Say equals normal CDF. Well, okay, there's two ways to do it, right? So let me be clear. There's two ways to do it, but the way we're going to do it is, normal CDF, and then we're just going to write down what the values are. We have the lower value. Remember, it's lower, upper, mean, standard deviation. So lower equals, the lower value is 68, right? The 68 height for the woman. Okay, so look at that here. Lower, upper, right? And then The mean is 64. The standard deviation is 2.7. So lower, upper, mean equals, well, usually I write it out just to be safe. Right, the mean was 64, and the standard deviation is 2.7. And if you do that, you get approximately 0.0561. Okay, which is a similar result to what we got. All right, so let's show you this on the calculator. All right, so showing you how to do this, we had to hit second and then vars for distribution. You see it says DISTR, so for distribution. And then we're going to go to normal CDF, not PDF, okay? Always go to CDF. And then lower was 68, the upper is 70. Then go down to, this is 64, and then this is 2.7. All right, and then enter, and then you'll get the 0.0561, which is what we got. All right, folks, so we're going to be wrapping this up here. So just a couple of things then. For continuous random variables, the mean is found by finding the point at which the area under the density curve would balance if it were made out of solid material. So how would we balance it? The mean is easy to find in symmetric density curves because it is located in the middle, right at the center. The standard deviation is harder to find, but it's easy for the normal distribution because we can locate it from its inflection points. The inflection point, by the way, for the exact calculation for mean and standard deviation for other density curves requires integral calculus. So you need to integrate in order to be able to find the exact mean and standard deviation when you're talking about other density curves. So that's why we're really going to be focusing on uniform and mostly on normal distribution. Okay. I would say most of the time it's going to be normal distribution, but the mean is in the middle for the normal distribution because it's symmetric. Now, to get the standard deviation, you need to find the inflection point. The inflection point is essentially the halfway point between the maximum and the minimum. Okay, so that halfway point, if you will, where the curve goes down and reaches its minimum point, I guess you can say, and reaches its maximum point, that sort of halfway point is the inflection point, okay? And that's how you can approximate the location, and then the distance from there to there is your standard deviation, okay? So that's how you can calculate that. So this is important to know because in certain multiple choice questions or certain things, they'll ask you, they'll give you curves, and then they'll say, okay, what is my standard deviation for this curve? And they won't really give you the value. They won't really, you'll basically need to know this idea, this concept of like where the first sigma is in order to be able to like proceed. And so you need to know this concept in order to answer that type of question. All right, guys, that's going to do it for the video. Hope you found this useful and informative. And as usual, I'll see you in the next one.